geometric setup, we know that the path difference between adjacent rays is given by d sine theta. Theta's like that. Okay. So even if you write down nothing else in a diffraction grating question, write down this. Right, this is the diffraction grating equation. Even if you were to get no further, you would get a mark for writing down that. Okay, so please just do it. If you spot the words diffraction grating, write that. Okay, so we've got some numbers. So we've got 500 lines per millimetre. This is the thing that is going to give us D. We also know that we're looking at a particular order of diffraction, the first order maximum, and we're told that that happens at 10 degrees. Okay. So we can figure out that lambda equals d sine theta over 1. Right, let me first figure out what d is. So d must be, so 1 millimetre, 1 times 10 to the minus 3 metres over 500. Right, that's the distance between the lines. And that is 2 times 10 to the minus 6 metres. Right, so 2 times 10 to the minus 6 sine 10 degrees over 1. I'm just going to get my calculator out. Right, 2 times 10 times sine of 10. Yes, I'm in degree mode, good. Right, so that is roughly 3.47 times 10 to the minus 7 metres, so about 350 nanometres. Okay, that's quite right on the edge, really, of the visible. There's nothing in this question that says we're necessarily in the visible. Visible's kind of 350 up to 700. But I think if you were very far away from the visible, you might want to go back and just sort of check that you've not done anything wrong. Okay, but I know this is right because I've checked this carefully, so we'll move on. Okay, so what we're asked for is not lambda and not even the frequency, but we're actually asked for the angular frequency. We're asked for that. So that is 2 pi c over lambda. You'll have a value for c in your data sheet book. Probably use that value if you can, because that is the numerical value that the examiner will have on their mark sheet. So if you want to put them in a good mood, use the number they will have used. Okay. So you've got to calculate that. Okay, so that is roughly equal to 5.4 times 10 to the 15 per second, radians per second. Okay, and even I'm confident that we've got 4 out of 4 there. Okay, where do the marks actually come from? Right, well, one will be just for writing this equation, right? One will be for working out the value of d correctly. One will be for working out the wavelength. And then the final one will be for doing actually what they actually ask you to do. Okay, so this, do read the question carefully, because the fact that it's asking for angular frequency, I could imagine, could be quite easily missed, in the middle of sort of the stress of exam and, trying to read things quickly. Really try and, make sure you read the question properly. Yes, it's only worth 1 mark, but it's a stupid 1 mark to throw away just for not reading the question properly, right? And it's easy to get to that mark if you read it. Okay, so now we're on to the long question. So, everybody happy so far? Okay. So the long question typically can go one of 2 ways. So either it will be a question that is fully optics, and it perhaps has several different bits to it, all based on optics, but probably the lower down bits, the bits at the end of the question, might be things you've not seen before. You know, often it starts with perhaps a standard proof, so you should make sure you go away and learn all of the proofs that you've been taught, you know, the single slit diffraction, the Snell's law, derivation, whether starting from Huygens principle or from Fermat's theorem, you know, all of those things, make sure you learn. The question will often start off by something quite standard and then perhaps get a bit more difficult, but always something that you should be able to do by adapting knowledge you have, or, you know, or just, you know, using the understanding that you have, right? It shouldn't be completely off the wall. So that's one way to go. Or sometimes optics questions are mixed with other topics from your first year course, right? So you might have a bit of optics, but have to draw on knowledge from other parts of the course as well. This one is quite a fun question. It's mostly optics. It's about setting light to a piece of paper using a lens, like using a magnifying glass. Don't know if you've ever done that. But there's a bit of differential equations in here as well, because of course this was on the CP4 course at some point. But it's not completely atypical that you might have to draw on other parts of the course in order to answer a question. Okay, so what have we got here? So we have this setup. So, light passing through a convex lens of focal length f, used to illuminate a sheet of paper some distance from the lens. The incoming light beam has a diameter d, okay, and is arriving from the sun. Explain why the light from the sun may be assumed to be collimated. Right, let's stop there for a minute. Okay, so the sun, what's collimated first of all? Well, it just means plane waves, right? Like that. So those arrows there are representing the light ray. Why can we assume that? Well, we're assuming the sun is a large distance away, right? It's supposed to be an S, right? Distance away. So we can basically treat it. This isn't really quite right, because the sun is actually quite close to us compared to other stars, right? But we're treating it essentially as a point source. At least as far as this problem goes, we're going to treat it as a point source, so which at large distances produces plane waves. And that is exactly the collimated beam that we're talking about. Okay. So if you just imagine, you know, that you do have a little point source of light, and of course this is producing spherical waves in 3 dimensions, but as long as you're far enough away, and we've seen this sort of drawing before in lectures, as long as you're far enough away, then these can be treated as plane waves. Now, if you're not quite convinced by that, because I think we can all see that the sun actually looks like a little disk to us, then, okay, you would be right. That is a sort of, it's not a perfect approximation, but at least the question is telling us, do assume this, okay, in order to allow us to move on. Okay, so what setup have we got? Right. So we're told that the light intensity coming from the sun is S, it's some number there which we'll use in a minute. Calculate the light intensity arriving at the paper and the illuminated area A as a function of the distance between the lens and the paper. Right, so what have we actually got going on? We've got, so this is going to represent my, sort of the circular cross-section of my incoming beam of light. We've got a lens here, and because this beam is coming in parallel, this is all going to be focused down to some point at the one focal length away from the lens. Okay, and okay, I've got to put my paper somewhere. Let's put it over here, let's say. So that distance that I'm drawing there is the L shown on the diagram. And we want to figure out what is the so I'm going to label the radius of this sort of spot on the paper r, and we want to calculate pi r squared as one of the things that the question asks us to. And we also know that this distance here then is L minus F, okay? Often drawing a diagram is actually really helpful just to help you visualise what's going on. You're not asked to draw this diagram particularly, but it's very helpful to visualise what's going on. It might even give you a mark, you know, if you then fall apart and don't do anything else, you'll probably get a mark for having done this. Okay, so first thing we're going to work out is what is this area? So again, it's a similar triangles kind of question. So I know that that is also equal to that. So my radius of my spot is d over 2f times L minus f. And so the area of my spot is pi d squared over 4f squared L minus f squared. Okay, so that's one thing we were asked to calculate. Something I should have said, sorry, when I was drawing this diagram, the one at the top there, I won't pull the screen down, I said, so we've got this collimated beam of light, it's going to be, because it's coming in parallel, it's going to be focused down to the focal point of the lens. My arrows are very badly aligned, I really hope you've corrected that. F is the distance from the centre of this circle to where it goes to a point. Right, and I said it goes down to a point, and then I've let it diverge again and sort of cast its circle on the paper. Right, why was it that I knew that this thing, I could draw this thing as if it's coming down to a point? This is what happens in perfect, ideal geometric optics, right? And it's true as long as we don't consider diffraction effects. Okay, so the question is, how did I know that I was able to ignore diffraction effects at this point in the question? Okay, and there are two clues to that. One is that this whole thing, where I've had to do about three things, first explain the collimatedness, then calculate the area, and then in a minute I'll calculate the intensity. It's only worth 5 marks, and so that suggests you probably are not supposed to do anything too complicated, but more, if you were to flip to the end of the question, as I'm just doing here, and of course in the exam you'll have the whole thing in front of you, it's easier to see, you'll see that this part of the question is to do with now what happens when you do include diffraction effects. The clues there are give a realistic estimate of the maximally achievable intensity, blah, 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 taking into account the resolution of the lens. That should tip you off, oh, now I've got to think about diffraction. With the implication being that in the first part, we don't have to. In the first part, we're considering pure geometric optics, okay? So try and read through the whole question as well. If anything's a little bit ambiguous to you, do I have to worry about diffraction or not? Read the whole question, it will probably put the context for you, give the context for you. Okay, so we calculated the area. Right, now I've got to calculate the intensity at the paper. Right, so something we know is that the total power is going to be constant. So we're given the intensity arriving from the sun as this S, that is a energy per unit time per unit area. But what we're doing is squishing down the bundle of rays by putting it through the lens. We're not changing the power, we're not changing the energy per unit time, we are just changing the spacing between those bundle of rays, right? We're squeezing them more together. So what we know is that, let's introduce a symbol for power. So I know that my total power is this S times the area of the beam, of the incoming beam, but that's also going to have to equal the intensity I want to calculate times the R squared that I have just calculated. Right, so those things must be constant. So I've got I equals S d squared over 4r squared, and if I put in my value for R up there, what I've got is that it's equal to f squared over L minus f squared. Okay, a couple of sanity checks on this. If I were to place my paper at the focal point, Right. Bring this paper, pop it wherever the focal point actually is. Then you can see that my intensity is going to tend to infinity. Right, and that makes sense because you'd be putting it right at this point where you've focused down to an infinitesimal spot, at least in geometric optics. Another sanity check perhaps, if I made L equals 0, i.e. I put the paper right up to the lens, then I just get I equals S, also makes sense. Another small sanity check, right, everything is squared here, meaning that I could have my paper either side of the lens and I'm going to get the same answer, right? So that also seems all quite sensible. Okay, so we've done that, we've picked up 5 marks. Right, so now what we've got to do is they've given us an equation for the change in temperature of the paper, and some constants here we're given. Right, assuming that the ignition point of the paper is some value, Ti, find the range of distances L for which the paper will start to burn, and how long does that take? Okay, so what's going on here? We've got this rate of increase of temperature of the paper. This little c is going to be some kind of heat capacity, but don't worry too much. You'll get into more of that sort of thing in the second year, but anyway, it's a constant as far as we're concerned. This is the intensity that we've just calculated a value or an expression for, and this appears to be some kind of cooling term. Okay, so what we can realise is that if, or maybe I should phrase it another way, we will reach a maximum temperature, T max, when dt by d little t, d temperature by d time, is 0. Okay, so I'm going to work out an expression for this T max. So I've just put dt by dt equals 0 in there. And so that gives me, if I just rearrange that a bit, that gives me I over alpha plus T0. Right, so let me pause here and explain what I'm doing. Right, so this paper will heat up and it will achieve a maximum temperature when dt by d little t is 0. And what we're saying is that if that T max is greater than the ignition temperature, then the paper's going to burn. Okay, so that in turn means that we're going to have some critical intensity that we need to achieve, i.e. what I need is T max to be greater than the ignition temperature, i.e. I need I to be greater or equal to Ti alpha times Ti minus T0. Okay, and of course the intensity, because we've just calculated it, is dependent on L, the distance between the lens and the paper. So we're going to put that in here to give us some condition on L, which is what we're trying to figure out. Okay, so I'm just going to rearrange that a bit. L minus F squared, I'm going to bring that up, must be therefore less than or equal to SF squared over alpha Ti minus T0. And this is a squared, so I'm going to take the square root, but remember this should be a mod because it's not going to matter whether the paper is one side or other of the lens, it can get the same intensity. So that is then root S, put F outside the square root, alpha Ti minus T0. Now have all of these numbers, 1370 over 250 times 506 minus 293 F. I also have F, but I'm keeping it as a symbol for the minute. Now, if you were to work that out, you would get that. Right. Now, F is 20 centimetres. We're told that in the question. So what I've got is L minus 20 centimetres is less than or equal to, if I stuck in 20 centimetres there, it would be 3.2 centimetres. And therefore, my condition on L is that it must be either less than 23.2 centimetres or greater than, the other way, 16.8 centimetres. Okay, so within that range, eventually our paper will start to burn. We've not yet calculated the time that it takes to do that, which is the thing we're about to do next. So does that make sense? Okay, so we've just used geometric optics so far, and then, okay, you know, our knowledge of power or energy conservation, and then done a little bit of maths to figure out this range of distances L. Okay, so how long will it take? Okay, this is the bit where you just need to actually solve the differential equation. So this is the thing we need to solve. And we need, so I need to, my limits are going to be from the ambient temperature T0 up to the ignition temperature. This is just a separable equation. It's integral from 0 to T. Okay. Okay, so let's do that integral. Right, so I've got 1 over minus alpha log I minus alpha T minus T0 Ti T0 equals T over C. Right, I'm going to take that minus away and put it there. Okay, so, oh, actually, I'm looking for T, aren't I? I'm looking for T. I don't need to, yeah, sorry. No, it doesn't matter which way the minus sign is. Right, so T equals minus C over alpha log I minus alpha T minus, oh, I've done something wrong, haven't I? Because I've not put in the limits yet. Sorry. Ti, apologies. And then that will be over I, won't it? So I'm going to put in a 1 and put the I over there. Right. Check that I've not done anything wrong there. So that's a 1. Right. Nearly forgot to put in my limits. Sorry for that. Okay. I think that's correct. But if unsure, we can do a couple of sanity checks again. So what if I made my T ignition be the same as the ambient temperature? Right, then I would get time T equals 0. That makes sense. Okay. What else? I itself has this expression. Right, I've not put explicitly in this expression yet, but that's what it looks like. So again, if I made LBF at the focal point, if we've got the diagram again, well, that's not a very helpful diagram. Right, if I put the paper at the focal point, we get this intensity going to infinity, right? So once again, we'd have T equals 0. So it all kind of makes sense. So I'm reasonably confident that that is correct. The one thing we can't really do is work out an actual value for time because we've not been given a value for L. We could, if we wanted to, already work out the range of times for the range of L's that we worked out, but I don't think the question actually wants it. I think it did want this expression at this point. Okay, right, we're going to have to do the last bit quickly. Right, so now, just for the last 6 marks, we need to think now about diffraction. So it says, explain what happens when L equals F. Well, we've talked a lot about that already in terms of the sanity checks and things that I was saying to do, verify that things make sense. So we've said it already, so I won't write it down again. But if L equals F, according to this purely geometric optics model, we would get an intensity of infinity, right? The paper would burn immediately. So write some words to that effect. Or in fact, I will. Right, so when L equals F, spot would be a perfect point or an infinitesimal point, except for diffraction effects, right? Which is, you know, obviously that's what this question, part of the question is leading you to. Right, so when you do have diffraction, what happens? So it says, give a realistic estimate now of the maximally achievable intensity, a particular wavelength. Right, so what we know is that rather than having a perfect spot, rather than having a perfect spot, we're actually going to get some circular spot of light instead. And if you remember when we talked about diffraction apertures, in particular circular apertures, you know that the half angle spread is given by that. Okay, so if it's a single one-dimensional slit, you do not have that factor, but if it's a circular aperture, you have that, and we discussed that, and you should know that factor, and it will probably give you a mark to include it, right? If you don't include it, you'll still roughly get the right answer, of course, but this is showing that you know what you're talking about. Okay, so that theta there, I will relabel as delta theta, because that's what I mean. Right, our paper is at the focal point, but rather than a spot, we're going to get a spot of that area, our A min is that, where R min is roughly the focal length times this delta theta, right? It's the delta theta times the distance that this spreading has taken place over. You can always assume small angles in this kind of calculation. Okay, so that's 1.22 lambda over df. And so what I now need to figure out is what is the maximum possible intensity achievable. Well, we just use the power conservation thing again, right? So I'm just using this again, where my maximum intensity is given when I have the minimum spot size. So Imax equals, so my pi's can go away, so I've got S d squared over 4 over this R min squared. So that's 1.22 lambda over d f all squared. So I've got S d to the 4, 4 on the bottom, 1.22 f lambda squared. Right, now you have all these numbers, you've got f, you've got a lambda, you've got d, you've got s. And so what that becomes is that. Okay, so that is our actual realistic, pretty large, but it's not infinity. So that's our maximum achievable intensity. And then we just have to do the final step, which is actually put that value into our equation for t that we had up there. So 1 minus alpha over Imax ti minus t0. Put in the numbers we were given. This is all in the question. 1 minus 250 over the thing we have just calculated. 506 minus 293. And that turns out to be about 0.16 milliseconds. Don't know if any of you have tried to set light to a piece of paper, have you? I've never done it that fast. So what, okay, I mean, what in practice probably prevents you from doing it fast? Well, you're probably not generally putting the paper right at the focal point. You know, you're probably not getting the maximum intensity. The sun might be a bit faint, a bit cloudy that day. Even if you are, of course, the sun is not, I think the biggest one is the sun is not a point source, it is a disk, right? So you're not quite getting that, that amount of intensity. Anyway, that's the answer. Go away and play with magnifying glasses. I'm going to say that because I'm not sure, I'm going to give myself that. I think that gives me that. I've not quite proceeded to the second year. I better do another couple of questions. Okay, right, that's it. Now, okay, we're at the end of the lecture today, but if you do have questions, you know, you can feel free to, well, I'll be here for a couple of minutes, and feel free to email me as well. Okay, thank you very much.